Okay. So I figured I would record a very short video to go over limits involving exponential functions, log functions, and trig functions. Actually, just when it comes to exponential functions, I mean e to the x. When I talk about log functions, we're focusing on the natural log of x, which is the log with base e, and then trig functions, I mean sine, cosine, and tangent, okay? Now, first of all, let's just recall the shape of these graphs. And I already, hopefully you already watched the video going over the basics, but let's just review this. So we know that the graph of e to the x looks like this, and knowing the shape of the graph will allow you to find the limits. Like, you don't have to memorize this. So since this is the shape of e to the x, as x goes to infinity, meaning x grows in the positive direction, then e to the x is equal to infinity. But then as x goes to negative infinity, then we see that the limit as x goes to negative infinity, it's equal to 0. So that tells me that there are no vertical asymptotes, and e to the x has a horizontal asymptote at y equal to 0, because the definition of horizontal asymptote or a vertical asymptote, it's not going to change. And then every single exponential function has the point 0, 1, okay? Right, because if I plug in 0 here, I get 1. Now, the graph of e to the negative x, well, it's the opposite. Now, it starts from the second quadrant, decreasing all the way to infinity. Now, the limit as x goes to negative infinity, it's equal to infinity. And you can think of e to the negative x as 1 over e to the x, right? So if x goes to negative infinity, this is like 1 over something that is e to something negative. So you can write it on top, going to infinity, like growing a lot. And then the limit as x goes to infinity, it's equal to 0. So then again, we still have the horizontal asymptote, y equal to 0. Now, the graph of the natural log of x, we know that natural log of x is the inverse of e to the x, meaning if I do e to the natural log of x, I get x back, and this is the same as the natural log of e to the x, okay? Using the graph, we see that the limit as x goes to infinity, meaning x grows in this direction, it's equal to infinity. And then the limit as x goes to 0 from the right, and notice that the domain of the natural log is 0, not included all the way to infinity. So this is just negative infinity. So then we see that we have that, in this case, x equal to 0 follows the definition of a vertical asymptote. So it has a vertical asymptote at x equals 0. Now, we know what the graphs of sine and cosine look like. We've done a bunch of examples, but it's important to notice that, first of all, these are continuous functions, okay? Since they're continuous functions, by definition, the limit, right, continuous function, the limit as x goes to a of f of x, it's equal to f of a, so you can just plug in and you'll get the value of the limit. However, at infinity, we see that it's always bouncing in between negative 1, 1, and everything in between, but it's like not a single number. So at infinity and negative infinity, the limit of both cosine and sine, they don't exist. So this does not exist. This does not exist. This does not exist. And this does not exist. Perfect. Now we know that the graph of tangent looks like this, and we know that we have pi over 2 and negative pi over 2, and then every time you add pi, you have another vertical asymptote. So I'm going to say here that we have a vertical asymptote. Let me just move this a little bit down. We have vertical asymptotes at like x equals negative pi. Let me say dot, 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 negative pi over 2, pi over 2, dot, dot, dot. And again, we can use the graph of tangent to find the limit as x goes to pi over 2 from the left and the right, just for example, okay? So as x goes to pi over 2 from the left, the graph of tangent takes me to infinity. So from the left, it's equal to infinity. And then from the right, it's equal to negative infinity. And I'm calling this like a bonus limit. The fact that, again, at 0, the limit as x goes to 0, it's equal to the value of tangent at 0. It is just equal to 0, okay? Let's do some examples. If I want to find the limit as x goes to infinity, when we're doing the limit as x goes to infinity, this is the only time that we can take whatever grows the fastest in the numerator divided by the whatever grows the fastest in the denominator, and then take the limit as x goes to infinity of that. So in this case, 4 is a constant, so it's not doing that much. So the behavior of the graph at infinity, the top one, it's determined by negative the natural log of x. So you have to write this in terms of the limit as x goes to infinity of negative the natural log of x. And then in the denominator, we have 2 the natural log of x. And just like we do for rational functions, you can simplify the natural log of x and the natural log of x, and you get that at infinity, this is just equal to negative 1 over 2. Now, the limit as x goes to pi over 2 from the left, this is, e is a continuous function, and we saw a property that allows us to take the limit inside the function. So in other words, this is the same as 3e, and then the limit as x goes to pi over 2 from the left of tangent of x. Now we saw that the limit as x goes to pi over 2 from the left, it's equal to infinity. So then we have here that the exponent, it's going to infinity, right? So this goes to infinity. As a result, we have that the whole thing will go to infinity, because at infinity, e goes to infinity. Okay, so there are two things happening here. First, we have that the limit as x goes to pi over 2 from the left of tangent, it's equal to infinity, but we know that at infinity, e, it's equal to infinity. It goes to infinity as well. So the answer to this is infinity. I don't know if maybe changing and making a change of variables will make it easier to understand, but we're sort of saying that you can say let y be equal to tangent of x, then as x goes to pi over 2 from the left, y goes to infinity. So you can rewrite this limit. You can rewrite the limit as x goes to pi over 2 from the left of e to the, so 3e to tangent of x is the same as saying the limit as y goes to infinity of 3e to the y. And then we know that, one more time, since the graph of e to the x looks like this, then as y goes to infinity, this is just infinity. So it's another way. So then here we're just making a change of variables. Let me say here, by making a change of variables, and then the first way I did it, it's just like understanding the behavior of e without having to make any change of variables. So whatever makes more sense to you. Now, here we have that we know that the limit as x goes to infinity of sine of x does not exist. But we know that the limit as x goes to infinity of e to the negative 4x, it's equal to 0. So again, as x goes to infinity, this goes to 0, and this does not exist. So sometimes you have to check, like you cannot just say that the limit is equal to 0 or does not exist. You have to see if there's a way that this combination of functions, having a limit that does not exist and having something that goes to 0, when we multiply them together, maybe that limit actually exists. And whenever you see sine, a good starting point is using the fact that we all know that sine of x, it's always in between negative 1 and 1. So the fact that you think of this tells you that this is a good candidate for the squeeze theorem. And you know what the squeeze theorem says? You know that if you have a function, let me say squeeze theorem, let me remind you, let me use a different color for this. Let me use pink. Recall squeeze theorem. The squeeze theorem tells you that if the function g of x, it's in between f of x and h of x, defined near a, except maybe at a. So what I'm saying here is that I don't need the function to be continuous at a for this to apply. So except maybe at a, and the limit as x goes to a of f of x, it's equal to the limit as x goes to a of h of x equal to L, meaning the limit of the two other functions is the same, then the limit as x goes to a of g of x has to be equal to L. So now I have sign, so I need to find a way of writing this function in the middle of two functions. So what we're going to do is I'm going to multiply everything by e to the negative 4x. So what do I get? I get now that negative e to the negative 4x is less than or equal to e to the negative 4x sine of x, which is the function that we're trying to find the limit of, e to the negative 4x. I don't know if this is easier for you to see, but if you think about it, the fact that you have a negative exponent tells you that you can just bring it to the denominator. So maybe this way you can see what's about to happen a little bit easier. Because now now I have the first condition. Now I have that my function is in between two functions. I'm going to compute the limit as x goes to infinity of the two other functions. And then if I get the same value, then the limit of our function is the same. So I have it like that. I'm going to say since the limit as x goes to infinity of negative 1 over e to the 4x, think about it, this goes to infinity. It's like we have 1 over something going to infinity. So we get 0. It's equal to the limit as x goes to infinity of 1 over e to the 4x. Then, by the squeeze theorem, limit as x goes to 0 of the one in between, which is e negative 4x sine of x, has to be equal to 0. Perfect. Okay, I have one last example for you. I want to find the limit as x goes to infinity of the natural log of x minus the natural log of 1 minus 2x. As x goes to infinity, this goes to infinity, and this goes to infinity. The problem is that infinity minus infinity, we don't know what that is. It's called an indeterminate form. So the first step is to recall the properties of logs, and we know that, I'm writing this for the natural log, but this works for any given base of a logarithm. So I'm going to use the fact that a difference can be written as a quotient, as a division. So that's my first step. Go back to black and say this is the same as the limit as x goes to infinity of the natural log of x divided by 1 plus 2x. Now, we know that the natural log is a continuous function, so I can bring that limit inside. So this is the same as the natural log of the limit as x goes to infinity of x over 1 plus 2x. And since I'm taking the limit as x goes to infinity, I can just take the limit of the quotient of the leading terms. So this is the natural log of, let me make sure that I write it in blue so that you see it's important. You have to write things in terms of the limit, otherwise it's not true, right? It is not true that x over 1 plus 2x is equal to x over 2x. This is only true, this is not true. This is only true in the limit. As x goes to infinity, actually. Just as it's only true when you take the limit as x goes to infinity. Now, I'm just going to cancel this and this, and I get that the final answer, meaning the limit as x goes to infinity of the natural log, like this whole thing, it's equal to the natural log of 1/2. That's it. All right, hope you enjoyed it. Bye-bye.